Hello, everybody. Welcome back today to calculus. Today we will be talking about rotation of a region about a line that is not the axis. So maybe like say the line x is equal to a and also y is equal to a. Because in the previous section we learned about how to solve for the volume using the disk method and also the washer method. So it's basically the same idea, but except your rotation is no longer about the axis, but rather just some sort of horizontal line or vertical line. In addition to that, also what about finding the volumes of solids that are going to create cross sections that are not of rotations. So you'll see those in just a little bit, but let's go ahead and get to the first part first, and we'll go ahead and extend upon what we did in the last section. So here, in the first problem, let me go ahead and change this a little bit bigger. What I want to do is I want to find the following then. Okay, so I'm looking first of all the region bounded by y is equal to x, y is equal to 1 over x, y is equal to 1/2, and then also y axis, and also the line y is equal to 4. So you can see that region on the right hand side. What I'd like to do is take that region and I want to rotate it about the line x is equal to -1. I take that whole thing and find out what the volume of the solid is going to be. So as we said, we are no longer rotating about the x-axis or the y-axis, but instead it's just some other horizontal or vertical line. So in this case, the vertical line that I'm referring to is x is equal to -1, which is located right there. So hopefully you guys can kind of see that. Okay, so that's going to be my axis of rotation. So x is equal to -1. Now, as a result, what's going to happen is you're going to, first of all, let me just draw what it looks like so then that way you can have a better perspective. The first thing you want to do is whenever you're doing a rotation problem, draw the reflection of what the other part looks like if you were to take your region and rotate it or reflect it about that line. So over here on the left-hand side, you can kind of see that this is going to be the kind of like the y-axis right here. And then you also have the curve that's over here. And then you have maybe like say a point over here, and then you have like some other point over here. So here is that curve then. Okay, so this right there is going to be that region that is going to be the reflection. Now, that is going to be the opposite side. So the rotation, the volume that we're looking at looks like the following then, okay? So here, let me just go ahead and see if I can use a different color over here just so we get a better orientation. So the volume, after you rotate it, looks like the following, okay? So it basically looks kind of like a volcano, as you can see. So here is another cross section. So here is going to be the other piece. And then here, let me just kind of make a little bit of thickness so you can see that it is going to be a washer as a result then. And then maybe just draw one more for good measure. So here's the last piece of the cross section. And then you can create infinitely many number of these. Now, do you have to be this precise? The answer is no, but I like to make sure that you guys can see what is it that we're actually solving for. And on your homework assignment or on the AP test, you definitely don't need to do this. It's just, for your reference if you really want to. All right, but anyhow, this is the volume of the item that I'm trying to find for right here. This, volume of this volcano. So first of all, I'm going to go ahead and take one of these cross sections, and then I'm going to go ahead and put on the side so we can see how to kind of like dissect it and create some formula just like last time. So let me go ahead and refer to this cross section over here where it crosses the x-axis. Where it touches the curve. I'm going to go ahead and call it the point x comma y as we normally would. Okay, so let's go ahead and take that out and put it over here. So this is what it looks like. So there's the inner radius, and then here is the outer radius, and here is the small little thickness. Okay. Now, for the thickness part, hopefully you guys can see that this is going to be something that is stacked vertically. So what that means is that the thickness right here, that is going to be my delta y, okay, because they're all stacked vertically. Now, in terms of the rest of this, let's go ahead and draw the axis of rotation in there. So then that way we can have some sort of orientation. So here is that middle. And again, that is supposed to be the line x is equal to -1. what I'd like to do is, since this is a washer method, I need to basically refer to the outer radius and also the inner radius. Now, for the inner radius, that is going to be consistent because if you go back to my curve over here, right, you'll notice that the inner radius is always going to be this length right here, no matter where your partition is going to be. That length, it always looks like it's going to be equal to 1, so that's the nice part. So this is going to be my inner radius, which is going to be 1. So inner radius is equal to 1 then. Now your outer radius, now that's going to be a little bit different. The outer radius is going to be this portion. And that is going to be, let's see if I can kind of draw it on the picture over here. That is going to be the length from here all the way to here, or here all the way to here, and in here is all the way to here. Each time you'll notice that there's an inner part right here, which is consistent of 1. So we can kind of put that in there for that is part of the outer radius. But then you're also going to have to add this small little increment over here that is going to the curve. And that length is always going to be x because that is your horizontal distance from the y-axis to the curve. So what I'm saying is that your outer radius is going to be 1 plus x then. Okay, so now we can go ahead and put everything together. So the volume of the washer is going to be equal to the outer circle minus the inner circle. So it's going to be pi multiplied by 1 plus x quantity squared minus pi multiplied by 1 squared. So bigger circle minus a smaller circle. And then everything multiplied by the thickness because this is in 3 dimensions. So that is going to be the volume of my washer, and that is what's going to allow me to set up the integral then. So the total volume is going to be the sum of every single one of those washers. So the summation of this equation, and then I'm going to go ahead and factor out the pi that they have in common. So that's going to be 1 plus x quantity squared minus 1 squared, and then we also have delta y. And as we mentioned in the last section, as soon as you see a summation and you also see a delta something, then that's where the integral setup is going to come in. So my integral, taking the pi outside, looks like it's going to be dy because we have delta y. Vertically, we are going to go from the very bottom all the way to the very top. So that looks like it's going to be 1/2 because that's where the lower bound is, going up to the upper bound, which is y is equal to 4. So it's going to be from 0.5 all the way to 4. And then we also have this equation over here. Now, what I don't like about this equation, just like in the last section, is that it is in terms of x, but I would like for it to be in terms of y because my integration is with respect to y. So we're going to have to make a substitution. Remember that this x is referring to the curve over here, which is then where this equation of the curve comes in. Y is equal to 1 over x. So that is going to be my substitution then. So pi integration from 0.5 to 4 multiplied by 1 plus 1 over y quantity squared minus 1. And at this point, this is all just integration by hand then. So we'll just go ahead and do it once this time. But then in the future, I think I'm going to go ahead and let you guys do that on your own then. So first, I'm going to expand everything out. That's going to be 1 plus 2 over y, and then plus 1 over y squared, and then minus 1. The 1's are going to cancel out. So now you're left with something that's pretty simple for the most part, which you can integrate. So the pi is going to be carried over once again. The 2 over y, when you integrate it, that is going to be 2 multiplied by the ln of absolute value of y. When you take the antiderivative of 1 over y squared, that is going to be minus 1 over y. And then your boundaries are still from 0.5 to 4. So now we're going to go ahead and plug in the upper bound minus the lower bound then. So plugging in the upper bound, I see 2 multiplied by ln of 4 minus 1/4. And then minus for the lower bound, same thing. So it's going to be 2 multiplied by the ln of 0.5, and then we have minus 1 over 0.5 then. Okay, so clean this up a little bit more. So this is just a lot of trimming work. 2 times ln of 4. I think that's can be written as ln of 16 because I want to combine it with the other ln. The 1/4 we'll go ahead and leave alone. And then we have 2, which we can put inside. And that that 0.5, that's the same thing as 1/2. So then that means that this is going to be 1/4 then because it's 1/2 squared. And then you have minus 1 over 0.5, which is the same thing as 2 then. Let's see, you want to make sure everything's okay. Oops, I forgot the parentheses. So what that means is actually this guy turns into a plus 2 over here. So we got to be very careful about that. So let's see, pi keeps to carry over. Let's see, 2 plus negative 1/4, that is going to be 1.75. And then we have plus ln of, now these two combined together, that's going to be 16 divided by 1/4 because of the property logarithm. So my final answer is going to be 1.75, which I guess you can write 7 over 4, and then plus ln of 16 over 1/4, which is going to be equal to 64 then. All right, so that is going to be the volume of that volcano that we just found over here. Okay. All right, so now let's go ahead and move on, and we'll do another problem similar to it. But this time we're going to look at, I guess, a rotation about a horizontal line instead of a vertical line, just to see how that changes things. So in this problem over here, this time what we're going to do is set up the integral for the volume of the solid generated by rotation of the region given, bounded by y is equal to 8 minus x squared, and then y is equal to x squared, about the line y is equal to 10. So in this problem, we're just going to set up the integral. The solving for part, I can go ahead and leave that to you. Or if you want, you can use finite integration on your calculator to do so. But I prefer you probably just want to do it by hand. But anyhow, there's the region on the right-hand side. So you can see that it is shaded in blue. The red graph right there for the red equation. Oops, sorry. Let me go ahead and erase that a bit. Okay. Let's see. The red equation over here, that is going to be y is equal to 8 minus x squared. But whereas for the other equation, that is going to be y is equal to x squared. Now, looking at what we have right here, the intersection, hopefully you guys can see, is located at 2, 4, and also negative 2, 4. If you have to solve for it, then you're going to have to, if you have to solve for the intersection, then you're going to have to do it manually or use a calculator to do so. But unfortunately, this isn't easy enough for you to see. All right, so for this problem, we're saying we're going to take this region and we're going to rotate it about the line y is equal to 10. So here is that line right there. Now, once again, I'm going to go ahead and draw the image of the reflection. So then that way we can see what it looks like then after we rotate it. So let's see here. Let's see if I can do a good job of this. Looks like a unit of 2, so I'm going to go up by a unit of 2. Okay. And then we are going to go up about somewhere around here. So, you know, please, you can forgive me for this one, but this is what it looks like. Okay, so there is going to be one part. And then for the other one, looks like I went a little bit too far. So hopefully you guys can forgive me. My drawing kind of sucks, but well, like I said, you know, fortunately in your case, you don't have to draw it out, but I just like to draw it just so that you guys can see everything. Okay. So let's see, that I do believe is like somewhere around here. And then for the other part, just so I can draw it a little bit cleaner, looks like it's going to be somewhere around here. And you also have the upper part, which is going to be something like this then. So here is going to be the upper region, and there you go. All right, so that is going to be the part. And so once you rotate it about that line, which again is located over here at y is equal to 10, then you're going to get something, and this is where it's going to get a little messy, so bear with me. You're going to get something like the following then. So here is the shape of the volume then that we're looking at. Okay. So it looks kind of like, I don't know what's the best way to describe it. I mean, I guess it's kind of like a bowl with some sort of like a weird inverted part in the inside where it's kind of like empty. But there you go. Nonetheless, it looks something like that then. So I don't know, if you put it on the side, maybe it'll look kind of like a bowl. And then you also have a bowl out here. And over here in the middle, that is going to be empty. And it's going to be convex in like this then. Okay, But anyhow, that is going to be my really, really poor drawing of it. Okay, but the important thing, what I want to get out of it is the cross section. So then that way we can see what we're setting up for the integral. So let me go ahead and do a little bit of erasing. So then that way, not all of these, curves are going to obstruct my view as to what is it that I want to set up. So let me go ahead and take this part out so we can see a little bit better. So this time, let me go ahead and use black so you can see it then. My cross sections that I'm setting up would look something like the following over here. Okay, so here is that cross section. So here you can see it's curving downward, and then here you have another part right here. By the way, I'm pretty sure that by the end of this section or this chapter, you guys are going to be very, very good artists. So here is the middle part, which is supposed to be hollow. So there it is. Okay, so I'm going to go ahead and shade that in, and then you have a small little thickness right here, which is going to denote that we are going to use dx because all of these cross sections are stacked horizontally. All right, so there it is. Okay, so hopefully you guys can see that washer. I'm gonna go ahead and pull out that washer so then we can kind of like figure out what is actually happening then. So here is the washer then. Okay, that is just a generic picture, which is pretty much all we need. And just like in the previous problem, what we're going to do is we're going to draw the middle, the axis of rotation, which again is located at y is equal to 10. All right, so now we're going to have to do the same thing as before. We're going to have to figure out what is the inner radius and what is the outer radius. Okay, so let's see. Going by the bottom part, because that is where I'm getting my curve, let me go ahead and kind of like, draw on the side over here what's happening. So here you have kind of like that curve, if you remember. That curve is in reference to y is equal to 8 minus x squared. Okay. Now, the inner radius, if you can see it, is located right here. That is the length of the inner radius. Okay, so inner radius. Okay. Now, on this point over here where it touches the curve, that again is going to be where I call x comma y. So in terms of the length, right, of the inner radius, keep in mind also that the x-axis is down here. Okay, so that is going to be bottom part. Now let me just go ahead and change the color one more time. Okay, this length, the point from where the point is to the x-axis, that's normally what we call y. The inner radius is located above it, just so that it is below the line y is equal to 10 and also above the y value. So what that means is that the inner radius is going to be 10 minus y, because this whole thing is going to be equal to 10. This part right here is equal to y, so therefore this part, which is the inner radius, is going to be 10 minus y. Okay, so that is going to be my inner radius. My outer radius, the setup is the same idea. I do believe that it's also going to be 10 minus y, but the 10 minus y in this case is in reference to the other curve that is going to be down here, right? So this is going to be the curve down here. The equation that it's referring to is just y is equal to x squared. But the outer radius, let's see if I can kind of draw it once again over here. From that point, right, that corresponds to the outer radius, the lower part, that is going to be y, just like before. And then 10 is still going to be the entire length, so that means that this is going to be 10 minus y then. It is 100% of the time where if you find the inner radius and the outer radius, they are going to be kind of the same setup. So if you get like 10 minus y for one of them, the other one is going to be 10 minus y. The only difference is they're referring to different equations. So let's go ahead and set up our equation then. So the volume of this washer is going to be equal to pi multiplied by 10 minus y quantity squared, and then minus pi multiplied by 10 minus y quantity squared multiplied by the thickness of dx. And once again, keep in mind that for this one, we have to denote which y is which. The upper one right here, that's going to be my outer one. That is in reference to y is equal to x squared. Whereas this guy right here, that y is in reference to 8 minus x, 8 minus x squared. So once we have this equation, we can now go ahead and set up our integral. So the volume of the total is going to be the summation of every single one of those scenarios. And at this point, I might as well go ahead and make that substitution right now just to make it a little bit easier. So 10 minus x squared, and then minus, let's go ahead and factor out the pi. So then in the inside over here, we have 10 minus, in parentheses, 8 minus x squared. And then that is going to be squared as well. And the notation is going to be changed. It's going to be delta x. It's going to be delta x. So now we see delta x in summation, and that's where the integral comes from. So the integral, and then we're going to throw pi outside. This is going to be dx. So that means we're going to stack it horizontally. Horizontally from where to where? Well, it's going to be from negative 2 to 2 over here. So that is going to be my boundary. So negative 2 to 2. And then for my integration, well, it's just going to be what my expression is over here. So 10 minus x quantity squared minus, for the other one, looks like it's 10 minus 8, so that's going to be 2, and then plus x squared, and then that quantity is going to be squared then. Okay, so we'll just go ahead and leave it at that. That's going to be our answer. And if you want, we technically can take this and change it a little bit just to make our life a little bit easier if you are going to integrate it. And we're going to change it to 0 to 2 with a 2 multiplied on the outside, and then the inside is going to be exactly the same, because if you notice, the curve is symmetric about the y-axis. So that's why we can just go ahead and divide it into 2 parts and multiply by 2. All right, so that is going to be our setup for this one. Okay, now, if you need to take a break, I think you probably should. Now let's go ahead and move on to this next part over here, which we'll talk about how to find the volume of other solids. This time, that's not going to be a rotation. Okay, so in my case right here, what I'm going to have is the following. I want to find or calculate the volume of the solid with its base bounded by the curve y is equal to square root of x. So you can see on the right, the x-axis, and also x is equal to 4. So this is going to be the base of the solid. Its cross sections are perpendicular to the y-axis and are squares. So let's see if I can kind of draw that illustration for you then. So on the right, you can see the region which is going to represent our base. And what's going to happen is I'm going to create cross sections, right? And careful right here, cross sections that are perpendicular to the y-axis. So that means that somewhere over here, I'm going to go ahead and draw a cross section, which is perpendicular to the y-axis, because that's what they told me. And from there, what's going to happen is I'm going to build squares in this case, because that's what it's told. So then that means that that is going to be the base of my square, and then my cross section would look something like this. Now, it doesn't look very pretty because I'm trying to draw something 3D and 2D, but let's see if I can kind of, satisfy your curiosity by drawing it in 3 dimensions so you can see a little bit better. So here's y, here's x, here is that curve, right? Y is equal to the square root of x, and this is going to be that boundary of x is equal to 4. So we're going to go ahead and take this line over here, which is perpendicular to the y-axis, and we're going to build a square that is located over here. Okay, so that right there is going to be my cross section. Now, if I go lower, I can do the same thing right here. You can kind of see I can go ahead and build another square as well. So this is going to be the other part. And then let's go ahead and maybe do a few more just so you can see everything. So here is going to be another square for its cross section. And then all the way to the top, which is going to end up to be, I guess, almost like the smallest possible square. But in the end, well, that's basically what we have then. And if I can kind of like, draw a few more curves just so that I don't get like, too carried away, it's going to look something like this. Okay, so definitely a lot harder to see, but that's what it's going to look like that. So basically you have a whole bunch of squares that are going to be kind of like stacked like this, and then they're going to get smaller, and then smaller, and smaller, and smaller, and smaller. I'm sure there's a thing out there that is going to be this shape in the world, but I unfortunately cannot think of it for the life of me Like, what shape is that going to be that exists out there? But anyhow, that's the volume that I would like to find. Okay. Now, as difficult as this sounds, it's actually very, very simple. It's actually easier than all the rotation thing that we've been doing. And the reason for that is, well, they tell us what the shape of the cross section is. So we just have to kind of work with that and just build it according to what's given. Okay, so here, let me go ahead and draw the cross section as we normally would. So our cross section, we're told that it's going to be a square, which is going to be this guy over here. Now, again, this square is basically coming from this part over here then. Okay. Let's see. So square, that means that these are going to be congruent side. I want to find the volume of this square with a small little thickness. And the thickness is located right here. Okay, so that is going to be my thickness, which basically, kind of says that this is a kind of like a slice of bread or something. In terms of where that thickness is in my picture, that is going to be over here. So you can see that the notation over here is going to be delta y. We're going to stack them vertically. All right, so now we need to find the volume of that thing. So let me go ahead and write down right here. The thickness is going to be delta y. Okay. Now let's go ahead and not beat around the bush. Let's go ahead and try to find out what is this length over here, because I need this length in order to find the volume. The length, according to my picture over here, once again, is going to be the following. Let me go ahead and erase some of this over here, so then that way we can kind of like, draw it a little bit better. Okay, so first, what I'm going to do is, again, where it touches the curve, where my cross section touches the curve, that is going to be where my x comma y is going to be. Now, if it helps, x is always the horizontal distance, just drawing it out to the y-axis. Whereas y is going to be the vertical distance, and I'm going to have to get rid of this guy a little bit. Okay, the y is going to be my vertical distance from here to the x-axis. What I want is this length over here, so that's going to be my question mark. Well, now we're going to look at the whole length over here, which is going to be equal to 4, because if you remember, we have that boundary vertically at x is equal to 4. So if this part is equal to 4 and this other part on the left is equal to x, then I do believe what we're trying to solve for is going to be 4 minus x then. Okay? And once we get that hard part out of the way, we're pretty much good to go. So the volume of the square, right, or the cross section, whatever you want to call it, is going to be 4 minus x multiplied by 4 minus x, so 4 minus x squared, and multiplied by delta y because there's a thickness to it. So the volume of then the, not the slab, but the total volume, okay, so let me go ahead and get rid of this guy right here. So the volume total is going to be equal to the summation of every single one of those slabs. So you can see, now that's where I'm going to set up my integral. And everything has been going according to plan, because normally whenever we set up these integrations, there's always an x in there and then there's always a y in there. So, it only makes sense. Okay, so now let's go ahead and set up the integral. The delta y is telling me that I'm going to do a dy. And that means that we're looking at it vertically from 0 all the way to 2 over here. So that is going to be my boundary from 0 to 2 of 4 minus x quantity squared. And once again, I don't like the x inside there, so I need to replace it with whatever that equation is going to be. And that is going to be y is equal to the square root of x. So if y is equal to the square root of x, then x is equal to y squared. So then my volume, if you can find out what is this integral, will be your answer then. 4 minus y squared dy. Okay. Unfortunately, I can't do a u substitution here because there is no du available. So I think what we need to do is multiply everything out. So 0 to 2, and then we have 16 minus 8y squared, and then plus, looks like it's y to the 4th, and then we have dy. Take the antiderivative of each piece. So 16y minus 8 over 3 y cubed, and then plus 1/5 y to the 5th, boundary from 0 to 2. So plug in the upper bound, which is going to be 32, minus 8 thirds multiplied by 8, and then plus 1/5 multiplied by 32. And then the lower bound looks like it's just going to be a bunch of 0. So let's see if we can kind of clean this up a little bit. Let's see, 32 plus 1/5 of 32 is going to be 6/5 of 32. And then minus 64 divided by 3. So I guess we can just kind of combine some of the like terms, whatever we can get. So 6 times 32, that is equal to 192 divided by 5 minus 64 divided by 3. And I think I'm going to leave it like that because I don't want to embarrass myself by not being able to do basic math. Okay. All right. So that is going to be the hard one. And now for this last piece right here, which is going to be kind of like the opposite of it, what we're going to do is we're going to set up but do not integrate the volume of a region that is bounded by a curve, again, with cross sections that are going to be of certain shapes. Okay, so for this problem over here, what I want to do is I want to find out the following then. Set up but do not integrate the volume of the solid with base bounded by y is equal to sine of x squared, a sine of x over 2, y is equal to negative cosine of x on the interval from 0 to pi, and its cross sections are equilateral triangles that are perpendicular to the x-axis. So on the right hand side, again, you can see the curve. So hopefully you can see where that region is. Now, what's going to happen is I am going to take cross sections that are equilateral triangles and perpendicular to the x-axis. So first, I'm going to go ahead and draw a segment that is in the region that is perpendicular to the x-axis, and that's going to be this guy right here. Okay, and from there, what I'm supposedly going to do is create a bunch of right triangles that are going to be three-dimensional. So hopefully you can kind of make that out that this is going to be a triangle that is going to be, I guess, erected upward, but not on 2D plane. Okay, and then over here, we're going to have another rectangle, and then over here, another rectangle, and all of them are going to be equilateral triangles. Over here is the last one, so it looks like this, and then let's draw one more for good measure, so somewhere over here that looks like this. When you combine them all together, you can see a picture of it that is going to be on the bottom. So it's definitely not something that's going to be easy to draw. Okay, but again, like I said, setup is actually not too bad because we have pretty much everything that we need. Okay, so first what we're going to do is we're going to go ahead and take the cross section, right, that we need, and we're going to find the volume of it. Okay, so this is supposed to be an equilateral triangle. Now, if it helps, let me just go ahead and do this on the side right now. The area of an equilateral triangle is supposed to be s squared root 3 over 4, just to kind of save us a little bit of time. So s squared root 3 over 4, where s is supposed to be the length of the side. So this is supposed to be the area, okay, of any equilateral triangle, okay, equilateral triangle with length s. Okay, so in this case, you can see where the triangle is located, and what I need to do is I need to find out what is the length of that s that's over here. Well, s looks like it's going to be the difference between the two functions vertically. So that means that this over here is going to be kind of like y2 minus y1, where y2 is in reference to the sine equation, and where y1 is in reference to the cosine equation. So that is going to be sine of x over 2, and then minus, but then becomes a plus because it's negative cosine of x. Okay? And now we're going to go ahead and throw that into our area equation, right? So that means the volume of the slab is going to be equal to sine of x over 2, and then plus cosine of x. And then that's going to be my s part, so that's going to be squared multiplied by root 3 over 4. The thickness, if you can see, my stacks are all horizontal, going from left to right. So that means it's going to be delta x. So that's going to be the volume of any one of those equilateral triangles. The volume of the total is going to be the summation of every single one of those not rectangles, but equilateral triangles that I created. So we're going to go ahead and throw a summation in front. And again, as soon as you have the summation, and then you also have delta x, then that's where my integration comes in. So that is going to be boundary, and then it's going to be dx. Now, for this problem, it's not from one intersection to the other. It's actually only from 0 to pi. So you got to be careful about reading this part. And I found out ahead of time, pi over here is actually going to be the intersection that is on the right-hand side. Okay, so that is going to be my integral from 0 to pi. And then now we also have the root 3 over 4, which I'll just go ahead and put in front. And in the inside, we're going to have sine of x over 2 plus cosine of x, and the whole thing is squared. So if we can go ahead and find out what this is, then we have our volume. Now, solving for this is probably not going to be necessary on the actual AP test because it is just going to be too difficult. So most likely, you'll be asked to use finite integration to solve for this, or maybe just to go ahead and set it up, and then we're pretty much done. Okay. All right, so that is going to be the last of that part. And here, I lied to you. There's a little bit more, right? Because I'm a horrible person. All right, so as I said, if you need to go ahead and grab some popcorn and take a break, go ahead and do so, but this is going to be lengthy. Here's the final, I promise, final problem then, okay? Here, what I want to do is I want to set up an integral to represent the volume of the frustum, not frustrum, of a pyramid with a square base of side B and also a squared of side A, and the height is going to be h. So there it is right there on the right-hand side, so you can see the picture of it. I'm pretty sure there's a candy that is going to be the shape of this. I just can't remember for the life of me what's the name of it either. I think it's like it starts with an R or something like that, Rolento or whatever. Anyhow, I want to find the volume of this, I guess, pyramid. Where the top part, you have a base of A, and that is going to be a square. And then the bottom part, you have a base that is going to be of length of B, and that's the bottom. And the height is going to be from here to here, which we are going to denote as h. So our answer, our volume, what I'm looking for, is going to be in terms of A, B, and h then. Okay. So for something like this, where you're not told, like, where is the cross section, where is it perpendicular to, you really have to build everything yourself. So what I did was I kind of did that right here, right? I asked myself, okay, where can I put the x-axis and where can I put the y-axis so I can see consistent cross sections that are going to be the same shape, so then that way I can go ahead and build something like I did in the previous problem. And looking at my picture right there, you can kind of see it, where my x-axis is located and where my y-axis is located. Because as soon as I put those there, you can see my cross sections, which are located right here. So this would be a cross section then that I'm referring to. And that cross section is going to be a square, so that's consistent. Remember, all cross sections should be proportional to each other. All right, so now in terms of how we're going to set that up, we're going to take this 3D picture and convert it into 2D so we can see it a little bit better. The top part over here, that is going to be the top part that's over here. The whole length is A, so that is going to be this part. Whereas the bottom part over here, you can see that the length is supposed to be B, so that's in reference to this part over here. Okay, what I need to do is I need to go ahead and draw the cross section within this 2D picture. So then that way I can know what I'm going to build. So that right there is my cross sections. And according to my picture, my cross section is that of a square. So most likely I need to take that guy, find the length of this horizontal piece, and then multiply it by 2 because there's another part to it, and then square it then. Nonetheless, let me go ahead and find all of that then. So first, we're going to go ahead and call the point where it touches the curve at the end, x comma y. And I know that this is going to be a line because if you notice over here, right, on the side of this frustum, it is going to be a linear path. It's like a trapezoid. So that's how I know it's going to be a line right there. So anyhow, first objective, find the equation of that line because that's definitely is going to be something that we're going to be using. So we came up with the following coordinates, a over 2 comma h, and then b over 2 comma 0, because remember the height is supposed to be h, and then a over 2 because that's only half the length over here, and b over 2 because that's half the length that's over here. Okay, so first I'm going to go ahead and solve for the slope, which is something that I did over here. So you can go ahead and pause the video whenever you need to take a look at it, but I'm going to go ahead and speed this up a little bit. Once we find the slope, then we're going to find the equation of the line. Now, normally we are done at this point and we can make some substitution, but I feel like we're going to need to go a little bit further because if you refer to earlier, if you remember, we said we need to find out what is this guy over here? What is this horizontal length? And that horizontal length, according to this picture, is going to be x because it is the horizontal distance from the x-axis to this point. So what that means is, for my equation of the line, I'm going to need to solve for x then. Okay, so let's see. We're going to go ahead and do that over here. So I'm going to go ahead and isolate x all by itself, and this is what it turns out to be. Now, let's see what happens then. Going back to my picture over here, let's go ahead and set everything up. We're going to go ahead and draw the square, which is supposed to be the cross section. Okay, we said that this guy on the bottom is supposed to be 2x because if you remember, 2x is the length from here all the way to here. Okay, so then now we're going to go ahead and draw the thickness part of it. Okay, so you can see how the square is going to be hopefully a somewhat nice equation. But my thickness is going to be delta y because we are going to stack this vertically. So the volume of the square, or this cross section, is going to be 2x quantity squared times delta y. Next, what we're going to do is find the volume of the total. So that means it's going to be the summation of every single one of those squares. So 4x squared multiplied by delta y. And again, there's x and there's y, so I know everything is okay. All right, so now let's go ahead and set up the integral then. So the integral is going to be 4, I'm going to go ahead and take outside. X squared dy, because I'm going to change those terms. My boundary is going to be, remember, we're going vertically. And from vertically over here, in the picture, you can see is going to be from 0 to h. So 0 to h. And then finally, what I'm going to do is I'm going to go ahead and replace that x with the substitution so that we can form some y. So that's what this nasty thing comes in. So my final setup is going to be a minus b divided by 2h multiplied by y, and then plus e over 2 quantity squared dy. And we're going to go ahead and leave it in this form. If you want to solve for this, by all means, go for it. Keep in mind that a, b, and h are supposed to be constant. Your y is your variable, so when you integrate, keep that in mind when you do the power rule. If you want to try it out, go for it. And then here, let me just go ahead and show you the answer so you can pause at any time to see what is the result going to be. And in the end, this is going to be the final result then. Okay. All right, so that was definitely a lengthy video. Thank you so much for watching, and I will see you next time then. So take care. Bye-bye.